Okay, we are back. We're going to talk now about epoxides. So just to refresh your memory, the way you form epoxides is by the addition of an oxygen atom to an alkene. And the way you do provide the oxygen atom is by the use of peroxy acids. The more commonly used one is MCPBA or M-chloroperoxybenzoic acid, simply because this happens to be a solid at room temperature. It's easy to measure and handle as well as store. So you can add this particular peroxy acid to ethylene, and this will produce your epoxide ring. And just to remind you of the mechanism, the way this works is that the peroxy acid positions itself such that this oxygen, where the hydrogen is bound, is positioned in front of your alkene. The alkene starts the attack onto the oxygen. The electrons of that oxygen-oxygen bond get broken and deliver onto the carbonyl carbon. But that also means that this carbonyl double bond has to break and have its electrons flow towards the oxygen. Then finally, this oxide that is freshly formed has its electrons attack the neighboring hydrogen. And once that hydrogen is removed, the electrons of the oxygen right here are delivered to the other end of the alkene to produce your epoxide ring. Alright, so that's one way in which you can synthesize ethers, but there's also a second way that involves a different addition reaction. So you can have here an alkene. This is 2-butene, cis-2-butene, reacting with dibromine. And as you may recall, the alkene attacks bromine. The bromine gets broken, forming bromide. And in the process, you form this bromonium ion. Now, if the synthesis is done such that water is used as a co-solvent, so you have it in high enough quantities, instead of having bromide attacking the end of the bromonium, the opposite end of the bromonium ion, you can have water performing that task. And if water attacks the bromonium ion, then what you're going to end up with is what we call a halohydrin, in this case a bromohydrin. Although at the present moment it's protonated, fully protonated, because the water comes along with its two hydrogens. So here's where the bromide comes in here to remove that proton and provide you with the alcohol functionality. So this is the bromohydrin molecule. And what you can see is that you do have an oxygen that is next door to the carbon where the bromine is located, and the carbon bromine bond is technically where the leaving group is located. So this halohydrin reaction can then be further utilized in the presence of a strong base like a hydroxide to deprotonate the alcohol. The electrons of that alcohol would technically go over to the carbon next door that has that leaving group, and the leaving group will then take off. So in essence, this is technically an E2 reaction that will form an epoxide by removing that leaving group next door to where the carbon-oxygen bond is located after the protonation takes place. So this is another way of producing your epoxide rings. Okay, so now what can you do with epoxide rings? Well, the thing is that as relatively simple as it is to make them, the truth of the matter is that the epoxide rings have a lot of ring strain because the bond angles right here are barely 60 degrees Celsius. Excuse me, 60 degrees. Why am I talking about temperature? So these are 60 degrees. And because the atoms, all of them are technically sp3 hybridized, the bond angle ideally should be 109.5. So what this means is that you're severely acute in terms of what the angle is, and this creates a lot of strain on this ring system to the point where it easily wants to be broken. So here's where the sodium alkoxide comes into play, because you can bring this alkoxide and react it with the epoxide, and what it will do is it will attack one of the carbons of that epoxide ring, that's breaking the carbon-oxygen bond, opening the ring so that you no longer have a cyclic structure, but now what you end up with is the freshly formed ether, but at the same time you now have a sodium alkoxide present. Now the sodium alkoxide could be reacted with a completely different alkyl halide such that you end up introducing a new alkyl group bound to that oxygen, and then this will be a diether molecule. So here we have the ether bound to one kind of alkyl, but on this other end we have a different alkyl, and this is actually kind of an elegant way of introducing um, different alkyls really onto those oxygens and making the ether asymmetric, which may be of use for whatever purpose you may have, synthetically speaking, maybe even catalytically speaking. But like any type of reaction that involves alkoxides interacting with alkyl halides, the alkyl halide has to be methyl or primary, otherwise you start undergoing eliminations. So that brings us to the following example. Let's say that we want to prepare the following ether, and then here the key aspect to notice is that on one end of this diether we have a sec-butyl group, whereas for the other portion of the diether we have a benzyl group. So there, the idea is that you do want two different groups attached to your oxygens. So that should bring the idea that perhaps you're going to want to use an epoxy ring to which you will add an alkoxide, and you'll follow that up by reacting the resulting molecule with an alkyl halide. All right, so now paying attention to what the molecule has, notice that the benzyl group here, this carbon is actually primary, right? So this is a primary alkyl halide. So that looks like um, a perfect molecule to be regarded as an alkyl halide in the synthesis process. The one over here is actually secondary, so that's probably not one that you want to treat as a secondary alkyl halide because you could undergo eliminations. On the other hand, you could treat this whole sec-butyl group as part of the oxygen. In fact, if you incorporate that oxygen, this could be the alcohol that you start with, sec-butanol. And then what resides right here in the middle, well, that's going to be your epoxide itself, right? So this whole thing here, carbon, carbon, oxygen, that will be your epoxide ring. And notice that here we have a methyl group bound to that group, which means that you'll have to have a methyl group bound to your epoxide. So let's start the process. So sec-butanol as the alcohol, an alkyl halide, in this case benzyl halide for your alkyl halide at the end of the synthesis, and we're going to have the methyl bound to the epoxide. So if we start that process, you could start first by having the alcohol deprotonated with sodium hydride to yield this sodium alkoxide, sodium sec butoxide if you want to be technical. And then you'll react this with epoxide ring that contains that methyl substituent bound to it. This will attack on the carbon that is least substituted. Okay, so it will not go for the carbon that's technically tertiary, but rather for the one that is primary. So it will attack that, which is the most accessible site. And when it attacks, the carbon-oxygen bond of that oxyrane ring will be broken. And this will produce sodium ethoxide, or excuse me, sodium alkoxide on the opposite end. Now, this is the oxygen that belonged to the epoxide ring. Now it's an alkoxide. Now that alkoxide is going to attack the alkyl halide that we're introducing now into the mixture. And so the alkoxide attacks that carbon, the leaving group chloride in this case takes off, you produce sodium chloride as a byproduct, and you end up producing your ether. Now, one extra thing I should mention is that in this type of multi-step synthesis, sometimes you can get away with mixing all these things at once, but oftentimes you do have to do this in steps. So basically, the first step will have to happen first and reach completion before you even add the alkyl halide, because if everything is present, there's a chance that the alkoxide will just attack directly the alkyl halide, and then you end up producing something else that you didn't try to make in the first place. So this is just a technicality, but as far as the mechanism goes, this is the type of thing you should be thinking about. Okay, here goes a third method. you could react your epoxides under acidic conditions, because the first thing was acidic conditions, basic conditions. We produced the alkoxide and we reacted the alkoxide with the oxirain ring. But what if we instead have acidic conditions, in which case we don't deal with the alkoxide, we just deal with the alcohol, but we do have acid present in solution. And this, by the way, will require that you only add a catalytic amount of acid, as you're about to find out. So here is a protonated alcohol, meaning that I've added probably already HCl or some other strong acid to the alcohol. And so the oxirain ring will attack that proton, yielding the electrons back to the oxygen and forming your alcohol. But now the oxirain ring is protonated. And what that basically means is that your carbons right here are now activated for attack. If the carbons of the oxirain ring are either primary or secondary, then the alcohol ends up attacking the carbon that is least substituted. Once more, all due to the fact that this carbon is most accessible. It has the least amount of steric bulk around it, so the alcohol can definitely attack that without much of a problem. At the same time, the carbon-oxygen bond of the oxirain ring will be broken, producing your neutral alcohol. But the ROH that came in attacking still has its hydrogen, so now it will form this oxonium cation, which means that now you have to have your solvent, your alcohol solvent, come in and remove that proton from that intermediate, and then the electrons will go back to this oxygen to give you a neutral ether functionality. And so this is one way in which you can form them, but notice the difference now. We are generating an alcohol with an ether functionality. And like I said, the ether can be primary or secondary. Technically speaking, you do not want to have more than 3 carbons bound to this oxirain carbon, because if that's the case, then something else is going to happen. And let me show you what that is. If you end up having a tertiary carbon, so this carbon has 1, 2, and 3 different carbons bound to it, and you do this under acidic conditions, the same step will be identical as we saw before, which is the protonation of the oxirain ring. But then what's going to happen is that instead of attacking the carbon that is least substituted, you will attack the carbon that actually happens to be most substituted. And this may seem to be a bit of a contradiction to what we just saw before. Like, why are we attacking that carbon? Now, if we do attack that carbon, we're going to break up this carbon-oxygen bond here on the right side, producing the alcohol over here. And then we produce this protonated version of the alcohol, which then the solvent comes in, attacks the hydrogen, and then those electrons go towards the oxygen to give you your final neutral ether. Okay, so then the question once more is, why are we attacking that carbon that is more substituted? What makes the tertiary so special that now is going to be accepting the attack of this alcohol? Well, the reason why having that tertiary carbon is kind of important to pay attention to is because you can form carbocations, right? And the fact that the oxygen here is positively charged means that you could be a resonance, move the electrons to that oxygen, and create a carbocation. Now, technically, this is not a resonance structure because you've broken the connectivity, but you could make that happen and produce this stable tertiary carbocation. And once that carbocation is made, it's now accessible to be attacked by your alcohol. And this is the reason why you end up attacking those tertiary sites. However, if the carbon in the oxirain is secondary or primary, you will expect to attack the carbon that is least substituted. Okay, so just keep that in mind. Otherwise, yeah, you get into trouble. Okay, so that's everything that needed to be said about the epoxide rings. In the next video, I'm going to show you how you make ethers via the oxymercuration demercuration route. So see you in the next video.